which means that every element in X for all X in A, let's say, okay, let's not do this. So pick an element, pick X1 and X2 from A. So we have a set A, then we have X1, then we have X2, and this is set B, and this is mapped using the function f. So if the function f is one-to-one or injective, then it should be the case that if f of x1 is equal to f of x2, then x1 equal to x2. So what does this mean? So this cannot happen. That's all it means. So if you look at this example, so this case cannot happen if the function f is one-to-one. That's all it means. Is that clear?
Children, please use the chat box to, at least say yes.
Okay, fine. So injective function is just a one-to-one mapping. And the next one would be surjective functions. So this is also known as onto functions. Okay. So what does onto function mean? Similar to the case above, you have A and B. But here in this case, every element in B has to have a pre-image in A. So what does that mean? Let's see it. So for all X in B, there should exist. So this is just a symbol for there exists. For all Y in B, there exists X in A such that f of X equal to Y. So what does this mean? So a function can be as follows. Say there are two elements here, x1 and x2, and it's being mapped to a specific element y. So can someone tell me if this is an onto function? So the only element in B is y. So is this an onto function? Yes. So this is an onto function because y is the only element in B and it has a pre-image. So pre-image of y is x1 and x2 here, because there are two elements which are being mapped to y. But for a function to be surjective or onto, so it need to only satisfy the criterion that there should at least be x1 or x2 as a pre-image. So here we have both, so it's a bonus. For a function to be just surjective, you don't need two pre-images, you just need one. I hope that's clear. So that's a surjective function. Is everyone clear about this? Okay, fine. So next is bijective function. So bijective function is simply a function f is bijective if f is 1 and onto. So that's all about a bijective function. I mean, I would encourage you to look at the meaning of this, but by the definition, as the definition goes, for a function to be bijective, it just needs to satisfy these two conditions. So it should be on 1 and also onto. Okay. So inverse is something which I would encourage you all to find out, and Do let me know in the next class what inverses are and when they exist. So this is an homework. This is a homework. Yeah. Okay. So that's all about functions. And yeah, so that's it for the recap as well, I guess. So someone is asking, Rahul, can more than one element in the domain of an injective function be mapped to the same element in the codomain? Okay. So that won't be a one-to-one function. So a one-to-one function by definition should satisfy this. So it will look like this. So this is how a one-to-one function will look like. So multiple elements can't be mapped to the same element in the codomain. And to make things more precise, like I haven't defined what a range, domain, and codomain is, but I hope you guys know it already. I hope, Rahul, it's clear for you. Yeah. Okay. So any more doubts? Or else we can directly jump to the new topic.
Please
Okay.
start with the new topics.
Okay. 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 So, to start with, first we look at what is the naive definition of probability. We had looked at this sort of informally in the last class. And how do you define it? So we looked at the pebble example, and we had many pebbles on a table. And some of you said that the sample space, which is usually represented by omega, is the set of all possible outcomes. So if the experiment here is to pick a few of these pebbles and see what they are in a random fashion. So if that's the experiment, the set of all possible outcomes just corresponds to the whole set that is possible. That is, each of these pebble is a possible option that can be picked up. So that would constitute omega. And then on top of this omega, we need to define what the events are. So some of you in the last class said that events are the items that are of interest. So the events are subsets of omega. So A is an event. Okay. So in general, any event is a subset of omega. And this is usually something of interest. And that's why we need events in omega. So when do we say an event has happened? So we say that an event has happened if at least one outcome is part of the event. Okay, so to look at a concrete example, so let's say if you pick one of these three pebbles, then you say that the event A has happened. So if you label these as 1, 2, and 3, so if 1, 2, or 3 is picked, maybe more can be picked. So if 1, 2, or 3 is picked, then we say that event A has happened. That's how you formally see an event. And to make things more precise, so this is not the actual definition of probability. This is just a naive definition that we'll do today. And to define probability more concretely, you need to know what is known as measure theory. So we won't be looking at measure theoretic probability. We'll be only looking at probability from a computer science viewpoint. And I mean, I would encourage you guys to look at what measure theory is and how measure theory would help us to do probability more formally. But we won't be looking at measure theoretic probability. We would be just looking at probability from a computer science viewpoint and what would help us. So maybe we look at some definitions from measure theory as we go on to look at some advanced topics. But in general, we won't be looking at measure theory at all. So the definition of an event can be made more precise and more mathematical using measure theory, but we are not going there. Okay. For now, this would be enough for us. So an event is a subset of omega. So events are basically subsets of omega. Okay. And how do we define probability? So that's the next question. So you define probability for events. So A is an event here, which is a subset of omega. And to come to the naive definition of probability, so it is just the number of favorable outcomes upon the number of possible outcomes. Okay, fine. So to understand this better, let's look at a concrete example again. So consider tossing two coins. Let's assume for now that these coins are fair. That is, the chance that you would get a head is equal to the chance that you would get a tails. And if you're tossing two coins, the what are the possible outcomes? The sample space would be either heads, tails, heads, or tails. All right. And I call event A to be the event that that is just okay. So can someone tell me what event A here is? As in, from an experiment viewpoint, what is A doing? Exactly. So at least one head. So A is the event which happens when there is at least one head, right? So now, according to the naive definition of probability, what is the probability of event A? Exactly, 3 over 4. And how is that? So there are three outcomes which can lead to event A. So that is the number of favorable outcomes, which is 3. And the number of possible outcomes are 4. So it's just 3 over 4. But there is a major catch to this definition. The problem is that we have made a few strong assumptions here. So when I'm talking about the naive definition of probability, I'm expecting this to be the standard definition that everyone would be using. But sadly, this is not the original definition. This is just a naive definition. And why is this naive? Because there are few strong assumptions that we have made. Can someone point out few assumptions that we have made on this definition, this particular definition? Okay, the first sort of trivial thing to see is that we have assumed that the sample space is finite. And why is that? So we have assumed that the sample space is finite. Okay, but do you guys see why? Okay, so the probability of A is defined as a fraction, and the denominator is the number of possible outcomes, which is the size of the sample space. So if the sample space is, say, not finite, then the probability of A would just be something like 1 over infinity, which is 0, or even not defined according to a standard definition. So this is not a standard definition because we have made the strong assumption that the sample space is finite. In general, for an experiment, the sample space can even be the set of all real numbers, which is clearly an infinite set. And one other strong assumption that we have made is that the outcomes of an experiment are equally likely. What does this mean? So equally likely means that here we have made a strong assumption that each of these events, so each of these events happen with equal probability. That is, there is no preference for getting an HH over an HT. And for this example, this comes from the assumption that we made initially that the coins are fair. So if the coins were not fair and we were tossing two differently biased coins, then this assumption is not valid, and hence we won't be able to use this particular definition of probability. I hope these two assumptions are clear for everyone. This is very crucial. And for many experiments, it would actually be the case that you're looking at equally likely possible outcomes and the sample space would be finite. And in that case, you can use the simple definition and get away with it. But there would be many real world scenarios where you'll have to use a much more standard definition. So are these assumptions clear for everyone? Okay. Okay. Please do feel free to interrupt in the chat. I'll respond immediately. Okay. So I'm moving on to see why counting is important. So this is the naive definition of probability that we have seen. Okay. Now let's see why is counting important here. So counting or combinatorics. So this is a very vast topic in itself, and I won't be covering all of it in this lecture because combinatorics is just a thing that we need to use in probability. So there's a course here in IISc which does combinatorics. So I hope everyone can understand how vast this topic is. But we'll only be looking at things that are important to us. And in the future, we may also see new topics from combinatorics. But yeah, this would only be a subset of a proper subset of combinatorics, and a very small one. Okay. So why is counting important? So let's say if the sample space is huge. So if the sample space is huge and we have to apply the naive definition of probability, we need to find out the number of favorable outcomes, right? So the denominator, the numerator is the number of favorable outcomes. And to calculate the number of favorable outcomes, it would be really hard because the sample space is very huge. I mean, it's huge, and the number of favorable outcomes can also be huge. So in that case, you can't list out all the possibilities like we did here. For example, for the set A, the set A is at least one head. We were able to point out the outcomes which would lead to one head. And it need not be the case that we can do this all the time. Sometimes the event itself can be an infinite size set. So we need techniques to actually count things when they are pretty huge. So when they are infinite size sets, we still don't know what is the definition of probability, because I haven't mentioned it here. But when, say, let's just, the size of set A is potentially huge, in that case we need efficient techniques to actually enumerate. We can't enumerate the size of A, so we need techniques to find out what is roughly, or like on average, the size of it in some arguments. And how do we do it? So let's say there are the sample spaces of size 10 to the 5, and A is an event which we need to figure out the probability for, and it can be of order 10 to the 3, but we need to figure out where exactly in 10 to the 3 it's of order 10 to the 3. So it's roughly around 1000. But if it's actually 998, we should be able to figure out that it's 998, right? And it's a hard counting problem. You can't just list out all the outcomes and do this. So you need efficient techniques to do that. So that's why counting is important in probability. So let's start with uh, a few basic ideas from counting. Okay. So we are only talking about the case when the sample space is finite. And large. It need not be large. It can even be applied to cases when the sample space is small, but yeah. Okay. That's the motivation. Now let's see what the multiplication rule is. Okay. So say you have to get an ice cream. You're here and you need to get an ice cream. The first choice you need to make here is whether you need a cup ice cream or a cone ice cream. Okay. There can be many other choices, just a specific example. And after that, once you've chosen whether you need a cup ice cream or a cone ice cream, the options I give you are, say, vanilla, chocolate, and then mango. Okay. And the same here. Okay. So what is the experiment here? So the experiment here is what are the possible ice creams and how many? This is the question that we need an answer for. Okay. And such questions which proceed in a sequential fashion. That is, the first experiment we had to do is to pick the cup or cone. And after that, once you reach a specific branch of this tree, so you can look at this as a tree which grows exponentially with each stage. So at the second stage, there are 3 leaves, and you have to pick one of these. So when you pick one of these 3, you get an ice cream. So this is what we are trying to count. So the number of ice creams here is 6 because there are potentially 6 options. When you look at the leaf nodes, these are the 6 possible ice creams. And how does this help for us in thinking about counting? So when you have experiments such that the first experiment has n1 outcomes, second experiment has n2 outcomes, and so on. So rth experiment has nr outcomes. Okay. In that case, the total number of outcomes would be just n1 times n2 times NR. So for this example, the answer would be 6. There are 6 outcomes. And you can see this as follows. It can be seen as 2 into 3 because the first experiment had 2 outcomes, which means that you selected a cup or a cone. And after that, you selected one of the 3, vanilla, chocolate, or mango. But you can also see it as 3 into 2. And the order of multiplication doesn't actually matter here. So if you chose the flavor first and then the cone, or the other way around, it's the same experiment. So this is a crucial idea for structured thinking when you have to solve a problem in combinatorics, and you see a sequence of experiments happening, and then you need to enumerate the total outcome of all the experiments proceed, like when you do it sequentially. In that case, you can just use the multiplication rule and figure out the answer. This is a very important concept, and there might be many other ways to think about the same problem, but this is one structured way that you can always do in your head so that you can be sure that the answer is right. Okay, so is this idea clear for everyone? This is pretty simple.
Students, is the idea clear?
Okay, nice, fine. So that's how you solve cases when you have sequential experiments. And the tree diagram is a tool which you can use for many such problems. And I mean, in general, for computer science people, at least you guys would have seen trees a lot, and trees help in structured thinking. So yeah, keep that in mind. So to see a concrete example for applying this rule, let's see the following problem. So the question is to find out the probability that when you have a hand of 5 cards, I mean randomly given 5 cards, what is the probability that you have 3 cards of same number and 2 cards of same number but different? So for example, this would be a valid outcome for this experiment. I mean, for this would be a valid event that we are looking at. Sorry, this would be an outcome which is in the valid event. Okay. Is the experiment clear for everyone? So you just need to find out the probability that when you are given 5 cards, that you get 3 cards which are the same and 2 cards again which are the same but of a different number. That's the question. So you need to find out this probability. Is the question clear to everyone? Okay. Can someone help me with the answer? So the idea is just to apply the naive definition of probability again. Okay. So let's call the event A as the event where we get 3 cards of same number and 2 cards of same number with a different number. And what was the definition again? So the numerator is number of favorable outcomes, but the denominator is pretty easy. So how many cards do you have in a full deck? Exactly. So you have 52 cards. And out of which, how many cards are dealt? 5 cards are dealt. So how many ways of dealing 5 cards from 52 cards? how would you exactly? So that's just 52 choose 5, right? So 52 C5 is just 52 choose 5. I mean, this is just another notation for writing it. So simple question, do everyone know what is choose 52 C5? Okay, let's do a brief quick overview of what C is here. So let's see what a binomial coefficient is. Okay, so binomial coefficient is defined as follows. So NCR or N this notation, both are equivalent, and this is defined as n factorial divided by n minus r factorial into r factorial. Okay, I hope everyone knows what a factorial is. And what is the meaning of this? Okay, this is a formula, but what is the meaning of this? You have n items, out of which you need to pick r items without considering the order. Okay, this is what n choose r means. And how do you see the formula? So the idea is to pick r objects first. So when you have n items, you have n choices for picking the first item. Then you have n minus 1 choices for picking the next item. We are just applying the multiplication rule here. And so on till you pick the rth item. So the n minus r plus 1 is the number of choices you have when you are picking the rth item. And note that in every step, one element is reduced because you have selected it for the previous one. Is this clear for everyone? How I got this? Okay, cool. I'm just saying you for the first item, for to pick r items, you pick the first item. For picking the first item, you have n options. For the second item, you have n minus 1 options, and so on. But if you look at this, the order sort of matters here. But for the problem we are looking at, the order doesn't matter. So what do? You divide it by r factorial. And you divide it by r factorial because we are overcounting r factorial times. So for example, say you have 1, 2, 3, 4, and 5. These are the particular r elements you picked. There might be a combination in this where it's just this. And there would be r factorial of such repetitions, and you just divide the total product by r factorial. Okay, is this clear? Okay, so now we just need to see how this formula would become the formula that I've written above. So if when you see the numerator, it can be written as n factorial by n minus r factorial, the numerator alone, and the r factorial from the denominator just stays. So this is how you get the formula. Okay, is the proof clear for everyone? Okay, fine. So this is what a binomial coefficient means. The problem that we need to solve is this. And the denominator should be clear for everyone by now, which is just 52 choose 5, because you need to pick any 5 cards without considering the order you pick those 5 cards. That's the possible sample, I mean the possible space that you consider. So you are only looking at these 5 cards, and whatever these 5 cards are, you need to find a specific pattern in these 5 cards. That's the problem. So you can pick 5 cards in 52, choose 5 ways. The numerator is what I need an answer for. Can someone tell me what the numerator would be? The numerator is just the number of favorable outcomes, which means the number of ways you can get 3 cards which are same, 2 cards which are same but different. Okay. Okay. So it's just this. So what is the first choice you have to make? So you have to first pick a card which you want to repeat it 3 times. So out of the 5 cards you have received, I mean, it's not with respect to the 5 cards you have received. You pick a specific card, and then you need to see how many ways that card can come from different suits. So there are 4 different suits in a card deck. I hope everyone knows that. And from these 4 different suits, you need to pick 3 cards. And after that, from the remaining bunch of cards, you need to pick 2 cards. That's how you proceed with the experiment. Okay. So let's look at this. So the idea is to first pick 3 cards of the same number. So you need to pick a number first. So how many numbers are available for you? In a deck, how many numbers are available for you? Can someone tell me that? Exactly, 13. So yeah, face cards are included, right? So 13 cards are available for you. And out of which you have four from different suits, which are of the same number. Okay. And out of these four, you need to pick 3. So that is 4 choose 3. Okay. And can you tell me the rest of it? So now we have picked one card which repeats 3 times. And this is the number of ways that is possible. Now you need to pick another card, another number, and you need to pick 2 of them. How do you do that? Exactly. So 12 times 4 choose 2. So yeah, this is the answer. So with this example, the multiplication rule should be pretty clear to all of you. Okay. If it's not clear, do look at the problem in slightly more depth. And if you have more doubts, you can let me know next class. Okay. So we have seen what the binomial coefficient is. Now let's look at what sampling is. Not sure if I'll have the time to finish this, but yeah. So I'm gonna look at what is known as the sampling table. So sampling just means picking items. So when you pick items, it can depend on the order or no order, basically. But another option you have is with replacement or without replacement. Right? So when you pick an item, you can put it back and run the experiment again. Or like counting, when you pick an item, you don't put it back. You can only count based on the remaining items in the set you're looking at. So these are the ways that you can do counting. And the question is, how do you fill this table? Filling this table requires the answer for this specific question. So how many ways can you pick k items out of n items satisfying the constraints? That is, for this box, you need to find out the number of ways you can pick k items out of n items with replacement when the order is important. Okay. So can someone tell me what this would be? Okay. So you have n items and you need to pick k items, and the order is important. So you can use the multiplication rule. Exactly. N to the k. Right. So what you do is you pick the first item, and then you see that you have n possibilities for picking the first item. And the second item can also be picked in n ways because it's with replacement. So you're putting that picked item back into the lot and picking again. So you have n items again, and you need to do this k times. So n times n times n times up to k times. So that is n to the k. Now, how do you do this without replacement? That is, you pick an item and don't put it back. You need to pick k items, not all the items from n. So you're close to the answer, but you need to only pick k items. Okay, so it would be like this. Okay, it looks like n factorial, but it's not n choose k without replacement, because n choose k does not consider the order. That's how we defined it. Yeah, exactly. That's n factorial by n minus k factorial. Exactly. Right. Right. So, as someone pointed out, when you don't look at the order, it would just be n choose k. Right. Okay. So the only box that we need to fill out of this is when you have n items and you need to pick k items with replacement, and the order is not important. Can someone tell me what this would be? This is a slightly more difficult idea. Okay, that's a good guess. Okay, so actually the answer turns out to be slightly weird. The answer is n plus k minus 1 choose k. Okay, I'm not sure if I'll have the time to do the proof here, why this is true, but I'll try to do it after looking at a few other concepts that I would like to introduce. So I would encourage you guys to find out how this works. And this this formula is pretty crucial, and it has sort of many interpretations to it. If time permits, we'll come back to it quickly. But yeah, so let's look at the next topic for how we would adjust for overcounting. So in some problems, you might end up counting the same thing over and over, because for example, say you only want to pick k items. So when we looked at the derivation of n choose k, we were picking the same item again and again for r factorial times, and here it would be k factorial times. So we divided it by k factorial to avoid overcounting. So another problem where you need to adjust for overcounting is this. So say you have a group of 10 people, and you need to split this into a group of 6 and 4, since it's we are talking about people, you know which person went into which group. That's a good way to look at it. And also labeling the items is always a good strategy when you do counting problems, because otherwise you might end up confusing whether you actually counted it twice or not. So the problem is, how do you split a group of 10 people into a group consisting of 6 and a group consisting of 4? How would you do that? Oh, nice. So someone actually said the answer for the previous sampling table thing problem. So the stars and bars. So this is a keyword that you can search for to figure out the answer for this. Yes, that's the right way of looking at it. Correct. So coming back to adjusting for overcounting, the problem is to split a group of 10 people into 6 and 4. And the question was, how many ways are there for doing this? Okay. So the answer is just simply 10 choose 6. Why? Because when you pick a group of 6 people, the other 4 are already determined. So from a group of 10, you just pick 6 people, and that's 10 choose 6 ways of doing it. But another way would be to actually just pick 4 people from this lot for picking the second group, and automatically you would be picking the other 6 people. Since we are counting the same for the same problem, both of the sides would be the same. That is, 10 choose 6 would be equal to 10 choose 4. Okay, so the idea here is you have 10 people and you need to pick 6 people. And by picking 6 people, you actually fix those 4 people as well. So the counting problem is solved. Another way of counting for the same problem is that you just pick 4 people and the other 6 people would be fixed. Since we are counting the same thing, both sides should be equal. So what we understand from this is that n choose k is same as n choose n minus k. Yeah. And this is a general proof technique that you can use for combinatorics. This is not proof by example. You're not just giving an example here. You're telling a story of how you came up with this binomial coefficient, and you're counting for some problem. And again, you're counting for the same problem, but in a different way. So it has to be same because you are counting for the same problem. So hence this equality holds, and this is a general identity that everyone uh, should know. Okay, is the proof clear? So this is an important identity which you can actually prove using algebraic techniques. You will have to expand n choose k, and then you will have to convert it to n choose n minus k. It's a pretty tedious task. But if you look at it from a problem perspective of splitting a group of people into 2 groups, you can easily see the proof. So this is a proof by a story. And this is a valid proof. This is not just a proof by example. This is a valid proof. This is a way you can give a proof within one line. And this is a very powerful technique which we'll see for a few other identities as well. Is the idea clear? So try to come up with a story why this left hand side should be true, and try to see if there is a way to count the same problem, and that would lead to the right hand side. So that's a valid proof. I hope that's clear. Okay. So Jasma ma'am,
Yes, sir.
ma'am, can I take 10 more minutes? Is that
Yes,
possible?
sir. Yes, sir. Please take, sir.
Okay. Would that be okay with the students?
I'm sure they'll be okay. They're very enthused anyway.
Okay, okay, okay. Just 10 more minutes, because I mean, I would like to show a few more identities that would hold in a similar fashion. Okay. Thank you, ma'am.
Yes, sir.
Okay. So going back to adjusting for overcounting, this this is a way for like writing proofs, and this is formal enough, and this is not just an informal way, but the story has to be precisely put for n people here, and you can't just argue with 10 people. Okay, so the next question would be, you have a group of 10 people and you need to split it into 5 and 5. Okay, so can someone tell me what the answer would be? It's a tricky question. It's not 10 choose 5. This is not 10 choose 5. But can someone tell me how to modify 10 choose 5 so that you get the answer? So you have 10 people, you have to split it into two groups of 5 people. Okay. Just think intuitively when you're telling the answer. So what happens when you do 10 choose 5? You just pick 5 people and the other 5 people are fixed. That was the idea for the above proof. Why can't we use the same idea? There's a problem with that. Okay. Oh, you're close. It's not 2 times. It's divided by 2 because you are over counting again. So when you fix 5 people, so let's say this is 1, 2, 3, 4, 5, and this is 6, 7, 8, 9, 10. When you pick this 5 people, when you do 10 choose 5, this is a possible outcome that you can have. But also, this is a possible outcome. So the same groups are being created here. So the groups that are being created here are the same, but you are counting it twice. So when you're counting it twice, you divide it by 2 so that the answer is corrected. So 10 choose 5 is right, but you have to divide it by 2. Is the idea clear? The problem here arose because 5 and 5 are symmetric. So when you pick 5 people, the other 5 people are fixed, and it can be the same 5 people that you are picking the next time. Is the idea clear? This is very important, and if there's any doubt, please do let me know.
Children, is the idea clear? Do you want sir to explain it again? Okay, it is clear, sir.
Okay. Thanks. Fine. So now we have seen why adjusting for overcounting is sort of an important problem. Now let's see this. Important identities and proofs. Okay. So I won't be proving any of the identities that I state using algebraic techniques, and that would just be tedious, and you'll just end up playing around with factorials and canceling out stuff from both sides. That's not a good way to do think about it, at least from my perspective, because you don't understand the meaning of the expressions. So one thing we have proved already is why n choose k is equal to n choose n minus k. We have seen this. So what is the proof idea? Choose a group of size k. The story is to choose a group of size k from n. So the left hand side is exactly that. But another way to choose the same group of size k is to choose n minus k people not in the group. Okay, so the idea proof is choose a group of k size from n. That is the left hand side, and the right hand side is exactly the same problem, but you can do it in a different way by choosing a group of n minus k size of people not in the group. not in the group that we want. So this is the group we are trying to count. This is the group that we are trying to count, and this is same as this group. But this group of n minus k is the group which we don't include in the group. So from the set n, you want a size k group, and you have n minus k people just being thrown out of the group. So if you count this group, you will actually end up counting this group again, because that's the same way to look at it. And n choose k would be actually counting this group directly. Is the idea clear? Is the proof clear for why n choose k is same as n choose n minus k? Okay, fine. So the next identity that we would see is this. So this looks like a pretty hard identity in the first go. And to solve this using algebraic techniques would take a long time. But if we have a story around it, you can solve it in 2 minutes. So what is the idea? Okay. So you have two expressions which you have no idea what to do with. So you're trying to make sense out of it. So how do you do it? So as before, we just look at n people. So consider n people. And the goal is to form a group of size k such that you fix a leader. A leader. Okay. So this is the problem that we are trying to solve. And there are two ways of looking at the same problem. The first way is to first pick the captain or the leader, choose the leader. And you can choose the leader from a group of n people in n ways. So anyone can be the leader. So n options are there. Now, after you fix the leader, now you have a group which is of size n minus 1, out of which you need to pick k minus 1. So you can do this in n minus 1, choose k minus 1 ways. Okay. And combining both these, it's exactly the LHS. All right. Is this clear? Why this is the LHS? Okay. So this is the LHS. So another way to look at the same problem is to first pick the group and then choose the leader. So pick the group. So how many ways can you do that? You have to pick a group of size k. So that is just n choose k. And then pick the leader from the group. So now you have a group of size k. And from that group, you can pick the leader in k ways. So that is just this. It is the RHS. So you have done the counting for the same problem, but in two different ways. So LHS should be equal to the RHS. So that's the identity. So this is the proof. I hope the intuition and the proof is clear. Okay, okay, fine. So now we are coming towards the end. So we'll see what is known as the Vandermonts identity. This is a slightly tricky one to prove using algebraic techniques. Okay, so this is the identity that you have to solve. And the naive way would be to just expand the left hand side and then convert it to a summation and then prove it. But that's very hard. That's not an easy task. So the easy way to prove it is by using this story idea. So what you do is construct the story around it. So you have M men and say N women. And from this, you have to form a size K group. And how can you do that? So you have a total of M plus N people and you have to form a size K group. So that is the LHS. And to see the RHS, what you can do is see this, that say if there are J men in the group and J is some arbitrary number between 0 and K, because if you are picking K people, then N minus, I mean, sorry. So if you have to pick K people, then K minus J would be women. Because that's how the group is formed. So you have J men, the rest would be women. And you are picking K people. So that is K minus J would be women. And how many ways can you do this? So you, out of M people, you are picking J people, and out of N people, which are women, you are picking K minus J people. Okay, but J we fixed as an arbitrary number, and J can range from 0 to K. So J can be 1, 0, 1, 2, 3, up to K. So each of this would count one specific formation of the group. So J equal to 0 would mean that there are 0 men in the group and all women. And J equal to K would mean that all men and no women. So if you add all of these up, it would just be the right hand side. Okay. So that's Van der Waals identity. And I would like to give a homework here, which is to prove this using a proof technique. I mean, the proof technique that we just uh, came saw. Okay, so this would be a homework. Don't try to expand both sides and solve it. That might be easy here because it's sort of easy to see that. But try to come up with a story proof how you can make the LHS equal to RHS. Okay. So I think that's all for today's class. I also had planned to show how you get n plus k minus 1 choose k when you have to pick items from k items from n with replacement and without order. So someone said stars and bars. That's the way to look at it. So if time permits, we'll see the proof of this in the next class. But yeah, this is a good thing to know. And there are a lot of interpretations you can have around this problem. So please Google and check what is stars and bars. Yeah. If you guys do that, then I'll skip this topic next class. So that's all for today. If you guys have any doubt, please feel free to ask now.
They're just noting down their attendance. The
Okay.
secret code is probability for today.
Okay. Ma'am, I don't think I got the link to this
Google
Google.
Classroom.
Yes, ma'am.
Yes, sir. So what happened is last week we had the session with Sri Durga ma'am,
Yes.
and we created a Google Classroom for game theory.
Okay.
And I tried adding Sri Durga ma'am's official email address that ends with IASC,
Haha.
but this did not accept. So I just wanted to check with you. There are two options now. Use your personal email address, or we'll create a Google group itself.
Okay.
Which, which one would you like to prefer, sir?
Anything works for me, but IIC mail should be working because we have Google Classrooms in our
IAC, is it?
yeah.
Oh, then you can create one and share the link with me. I'll share it with the children.
Yes, ma'am. I'll try to do that. I'll let you know within a few days. Is that okay? I'm
Yeah,
not
sure.
very sure because I haven't tried it out. So I'll let you know within 2 days.
Yes, sir.
Yes, ma'am.
Yeah,
Yes, ma'am.
thank you so much.
So if you guys have any doubts, please feel free to.
Yes, children, please ask if you have any doubts. And very shortly, we'll either have a Google Classroom or a Google group so that you can interact with sir and get your doubts clarified.
Yeah, once that's on, then things would be easier. You can just ping me there
Yes,
and I will.
yes,
Yeah. I think students are busy marking their attendance.
yes, sir. That's okay. So you can just try and let me know.
Yeah, sure, sure,
If the
sure.
Google Classroom thing works, then it becomes very easy because then even Sri Durga ma'am can create a
Yes, yes.
ma'am's
I'll
own
talk
Google
with her as
Classroom.
well. Yeah, yeah, I'll talk with her and then we'll let you know, ma'am.
Yes, yes, ma'am. Thank you so much.
Yeah, thank you.
Anand sir.
Yes, ma'am.
So we'll close the session for today. The
Yeah, yeah,
children
sure.
are very busy marking attendance, so their focus is now only on
No problem,
attendance.
no problem. Yeah,
So next week, once we decide on a classroom or group, I think then these children will be able to
sure, ma'am.
ask questions or
Sure, sure,
yes.
sure, sure.
Thank you
Thanks. So,
so much,
so
sir.
then I'll leave. Okay, ma'am.
Yes, sir. And I'll share the Zoom URL for the next Friday
Okay, ma'am.
shortly, sir.
Okay, ma'am. Thanks a lot.
Thank you so much, sir. Thank
Yeah.
you.
Bye. Bye, everyone. Bye.
Bye. Bye.